Hey everybody, welcome back. Today we're going to go over some Chapter 4 concepts, in particular the different inorganic nonsalts. The inorganic nonsalts are typically not going to contain carbon, and there are a few exceptions that we're going to talk about to that rule. If a chemical does not contain carbon, it's going to be considered inorganic. And since today's compounds also don't contain metals, we're going to call them nonsalts. Organic compounds, and that's something we're going to discuss in Chapter 5, these contain carbon but don't contain metals, so we would call the Chapter 5 compounds organic nonsalts. Okay? So what we're going to talk about today is inorganic nonsalts, which means no carbon and no metals. Alright? There are a few exceptions to the carbon is organic rule, and these include carbon dioxide, carbon monoxide, and the carbonate salts that we talked about in Chapter 3, but these are generally listed as inorganic due to their properties lining up with inorganic compounds versus organic compounds. So with that out of the way, let's talk about the various types of inorganic nonsalts. The first family we're going to talk about today is the binary nonsalts. And like the binary salts, these are only going to have two elements. They can have more than two atoms, but they cannot have more than two elements. And these are going to contain nonmetals in particular, with oxygen being omitted. Okay, we'll talk about when it contains oxygen here in a bit. These compounds utilize the prefixes di, tri, tetra. So that's di, tri, tetra, and penta to indicate the number of atoms present in the formula, where di is 2, tri is 3, tetra is 4, and penta is 5. And occasionally you'll see mono, which means 1. Okay, to name these compounds, we're first going to identify the element donating the fewest atoms to the compound. Then we're going to name the second element with the ending "ide." Okay, so let me show you guys an example of this. So if I have NH3, okay, I'm going to identify the element with the fewest atoms in the compound, which is going to be my nitrogen. So I'm going to list that. Nitrogen. And then I'm going to name the second element with the ending "ide" and the appropriate prefix. Okay? So, tri for 3. And instead of hydrogen, I'm going to call it hydride. So this is going to be nitrogen trihydride. Alright? And my hazards for these, my hazards for all of my binary nonsalts, I should say, is going to be that they're going to be variable. I'm going to have to look it up. Okay? In particular, nitrogen trihydride, you may also know as ammonia. That's the more common name for it. Okay? Corrosive, flammable, toxic gas. Not good. Alright? Alright, here's another example. We're going to have pH3. Alright, again, phosphorus has the lowest amount of atoms, so we're going to name it first. Phosphorus trihydride. The tri being because I have 3 of those hydrogen atoms. And again, my hazards are going to be variable. Alright, phosphorus trihydride is also known as phosphine gas, which, like ammonia, is one of the gases produced when we have a water reactive binary salt. Alright, in particular, this is produced when we add water to phosphides, your metal phosphides and whatnot. Alright, couple more examples. SCl4, sulfur having the least amount of atoms, sulfur, and I'll just write my chloride there. Alright, and because I have 4, I'm going to call this tetra, sulfur tetrachloride. Okay, hazards again, VH, and I really don't have a common name for this or anything, okay? And the last example is PCl5. Again, my phosphorus has the least amount of atoms, so I'm going to call this phosphorus. Leave my room for the prefix. I know it's chloride, and 5 is going to tell me it's going to be pentachloride. Okay, and once again, my hazards are variable. Alright, that's it for binary non-salts. Alright, so my next family is going to be the nonmetal oxides. Nonmetal oxides. And these are going to be just like my binary non-salts, except now I have oxygen. Okay, and these are typically going to be a product of combustion, so you may also see these called fire gases. Alright, and to name these, we're going to name the non-metal first, and then we're going to say di, tri, tetra, oxide. And you can also have mono and penta in there as well. Okay, so the primary hazards of these are going to include instant formation of very corrosive oxyacids, which we'll talk about next, when they come into contact with moisture. Okay, so these are going to turn into oxyacids whenever they come into contact with water, and these are pretty toxic as well, as you guys can probably guess from these being fire gases. Okay, so let's start off with NO2. Okay, and like we described earlier, this is going to be very similar to the binary salts. So I find my element that has the least amount of atoms, which is nitrogen, and I see that oxygen has 2. I have 2 oxygen atoms, so I'm just going to call this nitrogen dioxide. Okay, my hazards are going to be forms oxyacid when it reacts with water, and it's toxic. Okay, let's do another one. Alright, so I have sulfur, which only has 1 atom, and because I have 3 oxygens, I'm going to call this trioxide. Sulfur trioxide. Again, I add water to it, and I form oxyacids, and it's toxic. That's not to say that these are toxic only when water reacts with them. That's to say that when you add water to these, they are going to form oxyacids, but even if you didn't add water to them, they're still going to be toxic. Okay? Let's move on to a more common example. CO. Good old CO. This is going to be simply carbon monoxide. I wouldn't call it carbon oxide, I would call it carbon monoxide, meaning I have one oxygen atom there. Okay, and as you guys know, this is gonna be pretty toxic. This is one of our gases that we definitely know as a fire gas, a product of incomplete combustion. We go on CO calls all the time, both as hazmat teams and just as regular fire department duties responding to various CO calls. Okay, so we're pretty familiar with this one. And then one last example of a non-metal oxide is going to be PO4, and we can call this phosphorus since it only has one atom, and since it's got 4 oxygens, we'll call it tetroxide, or you can also see it as tetroxide. Same thing, okay? And my hazards for both of these, just like the other ones, are going to be that when it comes into contact with water, I form oxyacids, and these are toxic by themselves. Alright, that's it for non-metal oxides. Alright, the next group I'm going to talk about is the oxyacids, and these are formed by the combination of hydrogen with one of the oxy radicals that we discussed in chapter 3. So luckily for us, the oxy radical chart remains the same, and only the naming scheme is going to change. Okay, the same oxy radical chart that we used for our oxy salts is what we're going to be using again. Alright, so these are the oxy acids. And to name the oxyacids, we're going to have to figure out what the base oxyradical state is. And the base state is always going to end in ic acid. So my base state is going to be ic acid. If I add an oxygen plus 1 ox, I'm going to have per ic acid. So I could put a blank there and a blank there. If I take away an oxygen from my base state, I'm going to call it blank us acid. And then if I take away 2 oxygens from my base state, it's going to be hypo us acid. So you can see it's pretty similar to what I did for my oxy salts. Okay, and a good summary of your oxy radical chart in this naming scheme is going to be it's going to be found in supplement number 3. All right, so let's move on to some examples. All right, so first example is going to be chloric acid. Alright, so first things first, whenever I'm attacking something like this, is I'm going to look at my ending, okay? And I have ic acid. I don't have a per here, okay? I only have the ic acid, so I know that I'm going to be dealing with my base state. And in particular, looking at my base state, I'm going to have ClO3, okay? And all I do for this is I'm just going to add a hydrogen out there, okay? Just 1 hydrogen, all right? And the reason I only add 1 hydrogen is because that ClO3 has a -1 charge, okay? And this is something you gotta get used to, so I'm only gonna add 1 hydrogen there to balance that, okay? So you'll see what I'm talking about when we get into some of the other oxyradicals that have a -2 and a -3 charge. You'll see what I'm saying there, all right? So that is going to be chloric acid. Now, my hazards for all of my oxyacids, are going to be that they are corrosive. going to be toxic. And they are going to decompose to my non-metal oxides when they're heated. Okay, so just how my non-metal oxides, if I add water to them, they're going to turn into oxyacids. If I heat up those oxyacids, they're going to turn back into non-metal oxides. Okay, so just something to think about with that. So let me move on to another example. So instead of instead of chloric acid, now I have perchloric acid. All right. So what I can do is I look at my ending. I also look at my prefix over here, perchloric acid. So that means that I'm going to have +1 oxygen over my base state. I said earlier that ClO3 was my base. So now +1 oxygen is going to be ClO4 with my -1 charge. All right, I balance that out with 1 hydrogen, and I end up with HClO4 as perchloric acid. Okay, same hazards as before, corrosive, toxic. Oh, I forgot one up here. They're also going to be oxidizers because they have oxygen in them. Okay, so this one's going to be corrosive, toxic, and oxidizer, and it's going to decompose to a non-metal oxide when heated. Okay, all of these are going to have those same hazards. All right, so next example is going to be chlorous acid. All right, again, I look at my ending, us acid, okay, and looking at my oxyradical chart, I see that that is going to mean -1 oxygen from my base state. So my base is ClO3, my -1 -1 oxygen is going to be ClO2 with the -1. So chlorous acid is going to be HClO2. All right, and if I go even further, if I have hypochlorous acid, look at my ending, look at my prefix, and I know that that is going to be -2 oxygens. Base again is ClO3, -1, -2 ox. It's going to be just ClO with a -1 charge. So hypochlorous acid is going to be HClO. HClO. All right, let's do some more examples. All right, so sulfuric acid. Again, looking at my ending, ic acid. Okay, and so I know that that is going to be a base state, and the only oxyradical that I have in my chart that contains sulfur, okay, is going to be SO4 with a -2 charge. Okay, and so in order for me to balance that -2 charge out, I'm going to have 2 hydrogens. And that's sulfuric acid. Okay, and just like all the other ones, it's going to be corrosive, toxic, and oxidizer, is going to decompose to the nonmetal oxides when subjected to heat. Sulfuric acid in particular is some pretty nasty stuff. You should have a video on whatever LMS that you're using, whether it be Blackboard or Moodle or Canvas, where I've uploaded a video of it dissolving some toilet paper. I may have uploaded some other videos of it dissolving various things. Anyway, you can see the power behind sulfuric acid. It's particularly nasty. Okay. All right. Next example is going to be hyposulfurous acid. So I see the us acid, but I also see the hypo. So that tells me I'm going to be 2 oxygens down from my base state, where my base state is SO4 with a -2 charge. Take 2 oxygens away, and I have SO2 with a -2 charge. So to balance out that -2, I'm just going to have 2 hydrogens, S2, or excuse me, H2, SO2. It's going to be hyposulfurous acid. All right, next example is per phosphoric acid. Find my ending, find my prefix. So per blank ic acid indicates I'm adding an oxygen to my base state, where my base is PO4 with a -3 charge. I add an oxygen to it. Now I have PO5 with a -3 charge. To balance out that -3, I'm going to have 3 hydrogens in here. Okay. And you're probably wondering, well, wait, wasn't hydrogen kind of like a non-metal earlier when we were talking about binary salts, and some of the other earlier stuff? Hydrogen is kind of weird. Hydrogen is one of those elements that at times you'll see that it has a plus charge, at other times you'll see it has a negative charge. When we get into organic chemistry, it doesn't really have a charge. It just wants an electron to reach the duet rule. Hydrogen kind of, to be honest, it follows its own rules, and the only reason that it sits on top of lithium in group 1 on the periodic table is just to make the periodic table look somewhat symmetrical. Okay, but for the purposes of this class, hydrogen kind of follows its own rules. Okay, so just know that hydrogen's gonna not really act consistently throughout this class. Okay, let's do one final example. So I have phosphorus acid. Look at my ending. I don't have any kind of prefix, so us acid corresponds to -1 oxygen. My base state being PO4 with a -3 charge. Take away an oxygen, and I have PO3 with a -3 charge. And to balance that out, I'm going to have 3 hydrogens. H3PO3. All of those are going to have the same hazards. They're corrosive, they're toxic, they're oxidizers, and they decompose to the nonmetal oxides when they're subjected to heat. So the next family of inorganic nonsalts is the binary acids. And like we've seen with other binary families, these are just going to contain 2 elements. Okay. The binary acids are formed from hydrogen and a nonmetal from group 7, also called the halogens. also may see sulfur in there, which is technically group 6. Alright, and when they're in their gaseous form, the binary acids can come into contact with moisture and they can form acidic liquid solutions. Okay, and we're going to talk about the different naming scheme for the gaseous versus the aqueous solutions. All right, aqueous meaning that the gas has dissolved into water. All right, so when we name the gases, so when these are gases, we're going to name it hydrogen, plus the non-metal, we're going to end it in ide. Okay, so instead of hydrogen chlorine, we're going to name it hydrogen chloride. Okay, and when these are aqueous or liquid, okay, aqueous, we'll just say that's AQ. We'll put an L there for liquid. All right, instead of hydrogen, we're going to call this hydro. We're going to have the non-metal prefix, and instead of being ide, it's going to be ic acid. So instead of hydrogen chloride, now it's going to be hydrochloric acid. Okay, and some of these you guys have probably heard of before. All right, so we'll start out with some examples, and because group 7 is such a small group, there's only a few that we're going to talk about that you'll see out in the field, and then there's also hydrogen sulfide that we're going to talk about. So first one we're going to talk about is going to be HF. All right, and if we're talking about the gas, it's going to be hydrogen fluoride, and aqueous, we're going to call that hydrofluoric acid. Okay, and hydrofluoric acid is some pretty bad stuff overall. Okay, so hydrofluoric acid, you get it on you and it's going to start burning, probably not as significantly as hydrochloric acid would, but it has the ability to leach into your skin and get into your bones, start dissolving your bones. If it gets into your bloodstream, it can travel up to your heart, where it's going to throw off the electrical signal. The electrical signals in your heart, which calcium is a part of. Okay, sodium and calcium and all that. It's going to throw off the calcium levels, and you can go into cardiac arrest. So hydrofluoric acid has a particular reverence associated with it in the hazmat world, just because it is so dangerous, and you can have a very small amount that can cause issues. I know a lot of teams that are around the country that respond to HF, if they use level A suits whenever they're responding to HF, they'll decon them and then they'll just trash them. They'll dispose of them in hazardous waste, just because they don't want the chance of improperly deconning it and then somebody, a couple weeks down the road, reusing the level A and getting sick and dying from it. So it is some nasty stuff. In general, your binary acids, the hazards, are going to be that they are corrosive liquids. So when they are aqueous, they're going to be corrosive liquids. They're going to be toxic gases, so you wouldn't want to breathe in hydrogen fluoride, because you can imagine what it's doing to your skin. Imagine it doing the same and worse to your lungs. Okay, and this one isn't going to burn. We're going to talk about H2S in a little bit, which is the only one of these that does burn. Okay? Alright, let's go on to the next one, which is going to be HCl, and as a gas, we're going to call this hydrogen chloride. And when that gas comes into contact with moisture, which is all around us, right? So if this happens to have a release, if hydrogen chloride is released, if it comes into contact with the moisture in your lungs or on your skin, it's going to immediately turn into this when it contacts the water on your skin and in your lungs. This is going to be hydrochloric acid, which, by the way, is the same thing that is churning in your gut right now. This is stomach acid. Okay? Another example is going to be HBr. Gas is going to be called hydrogen bromide. And when it comes into contact with water, it's going to be called hydrobromic acid. Alright, and the final example we're going to talk about is the one from group 6. Okay, this is going to be H2S. Okay, and the only reason I've got the two hydrogens out there, very similar to what I was talking about with my oxyacids, is because sulfur has that -2 charge. And it's a gas. It's going to be called hydrogen sulfide. And I'm going to have an aqueous solution after coming into contact with water. I have hydrosulfuric acid. Okay, and the one additional hazard to this, so additional hazard, is that this actually will burn. So not only is it a corrosive liquid and a toxic gas, I should say, it will burn. Alright, and H2S you may also know as sewer gas. Alright, and if you've had any experience on a hazmat team before and you've messed with what's called a 4-gas meter, which is kind of the that's kind of our bread and butter tool on hazmat responses, you'll see that H2S is likely something that your 4-gas is monitoring for. It is a common gas that is produced from decomposition, and so down in the sewers where there's a bunch of waste that is decomposing in the dark, damp caverns of sewers and whatnot, you get a lot of H2S being formed, and it has that rotten egg kind of smell to it. Okay, you'll get called out to these occasionally. Normally either something has died or there is no water in the P-trap of, say, a toilet or a sink or a floor drain or something like that, and so there is a direct connection between the sewer and the interior of somebody's home or a business or something like that. So once you figure out, hey, this is H2S and it's coming from this floor drain, a lot of times you can just pour some water in, add a little bit of bleach just to clean up anything, any grime that might be down there, and you can go on your day and problem solved. Okay, just know that this stuff can burn as well. All right, so be careful when you're monitoring for H2S. All right, so the final group that we're going to talk about today is the inorganic cyanides. All right, as you can probably tell from the name, these are going to be toxic, just how they were whenever we were talking about our cyanide salts, our metal cyanides. Okay, and we'll see some more cyanides when we get into organic chemistry and hydrocarbon derivatives, which they are also going to be toxic. All right, two main examples we're going to talk about. Really, these are the only ones that you should see in your homework. Don't quote me on that though. It's hydrogen cyanide and cyanogen chloride. And my formulas for these: HCN, you probably know. HCN and cyanogen chloride, it's going to be ClCN. Okay, hydrogen cyanide and cyanogen chloride were both used as chemical warfare agents due to their extreme toxicity. And how they work is they pretty much just prevent the cells of the body from utilizing oxygen. So oxygen can be carried through the bloodstream and whatnot, but it's essentially acting as a bouncer to the club, saying, hey, you're not able to get in here, okay? And it throws out the oxygen. This happens for long enough, and ultimately it's going to shut down aerobic metabolism, and you have cell death, okay? Hydrogen cyanide, you probably are more aware of. It is a product of incomplete combustion, particularly when we're dealing with synthetic materials. Hydrogen cyanide is more on the rise. So, yeah, bad stuff, all right? But fortunately for you, these are the only hazards, or sorry, the only two that you have to know. Hazards, they're toxic. All right, so that's all I have for inorganic non-salts. Hopefully you have a better understanding of them now. The bottom of supplement 4 is going to give you a pretty good summary of all the families that we talked about today. And in chapter 5, that's when we're going to start tapping into the huge world of organic chemistry. All right, I wouldn't say that things necessarily get more complicated, they just get different. All right, and we'll be able to really expand on everything that we're talking about, and you'll see that possibilities are pretty endless when we're talking about organic chemistry. But we'll talk about that in the next video. So take care. See you then.